Hey everyone, my name is Shane Glass. I am the program manager for Google Cloud's Public Datasets program. In the back is Simon. Simon runs the Earth Engine Public Datasets program. Let me kind of level set here and say that they're different programs. Although Simon and I do work together a lot, we do share some datasets. We do some overlap. They're different things for different use cases. And what I want to do today is just kind of give you an overview of what the Cloud Public Datasets program is, how it can benefit you, and kind of what's the use case? And ultimately, what I want to talk about today is I want to talk about how the work that we're doing to democratize data access can make each individual's research, make everyone's research just a little bit easier. I don't have some wild notion that we're gonna like make everyone's life simple and easy, and it's not gonna take any hard work. But hopefully, we can take on some of that hard work so that you can focus more on what you do best. The goal here of being that like we'll focus on bringing the data on so that you can focus on your research, and ultimately like we want to help you tell your story, whatever that might be. In fact, let me start off by telling you a little bit about my story. And so I am the cloud lead for public datasets. Before this, I was working as a contractor for NOAA. I managed their public datasets program. Excuse me, their public data big data project. So we worked with providers to host copies of valuable NOAA data sets on the cloud to make it easier for people to access and use. If that doesn't sound familiar, don't worry. We still have 48 more minutes in the session, so it will by the end of it. I am also a data visualization enthusiast. And most importantly, I'm a public datasets user. My story for public datasets is funny in retrospect, but not at the time. My master's is in data analytics, and we spent every week we would go through a different type of model, right? So the professor would say, I don't know, build a support vector machine this week, which is fine, except it's not normally how you would approach that problem. Normally, you'd approach the problem by saying, okay, I have this data set. I have this question I want to answer. What's the best model to get me there? Kind of had to flip that on its head and say, okay, I have this model. Now can I find a data set that answers some question? And what I found was that the most frustrating part of the program I had, and this was, I kid you not, 10 hours a week, was finding data sets that were rich enough and featured enough to build really legitimate, like really great machine learning models, but not so complex that I had to become an expert in the field. I don't think anyone's surprised by the fact that I'm not a climatologist. I don't think anyone's surprised by the fact that I'm also not an oceanographer, a botanist, and a zoologist at the same time. So for me, this passion to open data and to make it easier for people to use comes from a really central place, a really personal, deep, pained place of my history. Um, and so that's why we're so passionate about this. And the other reason is that this is a really, really natural fit for Google's core mission. If the two words in blue there look familiar, that's because you've probably seen them before. Our mission here in the program is to maximize the accessibility and usability of high value, high demand public data assets through Google Cloud. Those verbs come straight from Google's mission statement to make the world's information universally accessible and usable. And so I think this is a really natural fit for who we are as Google, and who we want to be in working with our users. We currently have more than, I think the number is probably closer to 140 data sets now. But if I put 140 in there and I was wrong, I would have to come back and tell everyone I was wrong, and no one likes to do that. So more than 130. They are onboarded and maintained by Googlers, but we do make sure to reach out to data providers like the NOAAs, NASA's, USGS's of the world, to onboard those data and to kind of understand their expertise, with the goal there being that the data is really valuable, but so is the expertise they bring to the table. So can we help scale out their expertise so that users who access the data, one, get a copy that's structured and described according to best practices, but two, can fully understand what they're getting and what they're working with. So you can see a sample of some of our data providers here. It's a really classic like geo for good kind of data providers, right? Including OpenAQ, which is a nonprofit that does air quality measurement out of Annapolis. But we can also kind of take that one step further by blending that with other data sets and allowing for this kind of cross-functional research, or this kind of cross-expert collaboration by bringing in demographic data from the US Census Bureau or boundary data from the US Census Bureau, which we'll look at in a little bit, data from the World Bank or the UN Statistics Division about poverty or access to power across the world, and health information from the NIH. Can we figure out new things about healthcare? Can we figure out new things that we can treat based on these climatological factors? Or can we say, hey, we see an increased rate of childhood asthma when we see these specific pollutants. Now we can take that forward to policymakers and really start to tackle these challenges and really start to figure things out. So while we do have these kind of very classic geo data sets, I think being able to layer these other factors on top of them is something that we've done that I'm very proud of and that I think has been really helpful for our users. We have structured data sets in BigQuery, which we just talked about. We also have about 7 or 8 petabytes of unstructured data sets in Google Cloud Storage. Sentinel-2 data, which you can also get in Earth Engine, is available in its raw format in GCS. We just brought on the high resolution rapid refresh model from NOAA and NOAA's national water model as well. The HER model, the high resolution rapid refresh model, gives very, very fine grained modeling, atmospheric modeling over North America. And the national water model provides continuous stream flow for the continental United States. So whereas USGS stream gauges, there's 11,000 some odd points. I don't remember off the top of my head. This is more than 2 million points of continuous stream flow. So 2 data sets we're really excited about. The water model in particular, we're really excited to host the 40 terabyte retrospective data that is otherwise very difficult to access. There's a long story behind that that involves a Pelican case, failed hard drives, and Hurricane Nate, and some angry phone calls I had with an anonymous shipping company. But we did eventually get the data. We did eventually get it out, and that's something that both of these we're building a lowercase a archive of that so that they can be used to train machine learning models that can predict on the real-time data as it comes in. So I get a lot of questions about why would Google do this, right? Like what's in it for Google? And there are some selfish incentives, mostly so I can keep my job. But there are some other incentives here as well. We talked about it being a really natural fit for our core mission. And everyone here remembers the scientific method, right? You'll each be called up later to recite it in front of the whole group. If you don't, that's okay. Your secret is safe with me. I won't tell anyone's 6th grade science teacher. But this is kind of at a very high level. This is kind of what the data science process looks like, right? You discover the data set, you access it, you write a program to parse it, you load it into the database, you update, maintain, secure the data and the database, you manage access to the data, you update the data regularly, you link your private public data, you analyze it, you visualize it. That's a lot. And I don't know about you guys, but I don't have unlimited time on my hands. And so I think that, we talk a lot about the data science paradigm, right? Where 80% of your time is spent cleaning and preparing and structuring your data. And the other 20% of your time is spent actually analyzing and communicating your results. But what if we could flip that? What if we could reverse that paradigm such that 80% of your work, 80% of your time goes towards the actual science, the actual work, the things that actually make a difference in our communities, whereas we can spend 20% of the time cleaning data. And the idea there being that we'll take on these steps. So the Public Datasets program does these things. Manage, maintain, and secure a database is really easy thanks to BigQuery. I just get the product team to do all that, and then I kind of come in and use some of their storage. But other than that, we're doing all these things. We're updating the data regularly. We're working with data providers to let them know if something goes down. And the benefit there is for them is they don't have to receive 100 phone calls when a data set feed goes down. I'll call them up and say, hey, or email or whatever, and say, hey, this data feed is down. It's affecting hundreds of users for me. And I can speak on behalf of this kind of larger group and kind of push towards a resolution. And in the meantime, you guys don't have to worry about that. Y'all just do your analysis and you focus on the science. We're not going to meet every cleaning need and every preparation need, and that's okay. And that's why I say, 80-20 as opposed to 100-0. But for the most part, if we can take on the bulk of that, you can focus on this. You can focus on analyzing your data, on communicating, visualizing, and implementing the results. And this is what we all want to do, right? This is what I want to do. I want to analyze, and as a data visualization enthusiast, I want to visualize and implement my results. And so I think one of the things we look at and say it's kind of hard to do data science right now. It's especially hard if you're, for example, not a major corporation who can spend $250,000 on a goes downlink antenna. And that's assuming you're in the Western Hemisphere because that's where the satellite downlinks to. It can be very difficult or very costly, even though these data are technically free and open, to access the mechanisms that do that. So we think by democratizing the access to this data, making it accessible to everybody as fast as we can really eliminate some of that burden and some of that hassle. Okay, so you came for the demos. Now to the demos. So I want to walk through a few demos and a few different use cases. That was very bad. Feel free to laugh at me and not at the joke. That's okay. So I want to walk through a few different use cases. And the idea here is not necessarily to solve any like earth-shattering problems. If these demos solve earth-shattering problems, then we had some bigger problems than I realized. But just to kind of give you an idea of what's possible, both using BigQuery and Google Cloud Storage public datasets, and kind of get the gears going in your mind of, oh, hey, I could do that. Maybe I wouldn't do it the same way, but I could certainly do that. Or I could use that data set to do this or something like that. So let me switch over here on my computer, and I'll switch over to the podium mic as well. And let's walk through the first demo. So this first one is going to look at escape. Okay. Well, the first thing I want to do is I want to kind of walk through our data catalog, just kind of show you what's there. But typing this in takes you to our GCP marketplace. Now, GCP marketplace is the home to a catalog of a lot of things. This takes you directly to our data sets, which is one of the things I really love about it. And so this takes you to our catalogs. So here's our catalog of our data sets. You can see also in here there's patent public data sets, a different program, but same concept of public patent data that's available. And you can click through here and you can kind of scroll through these. We'll click on an example. Let's take the forest inventory analysis. And you can see in here there is an overview of the data set. We include sample queries for those that are in BigQuery. Or some sample use cases for those in GCS. And of course, a big giant blue button at the top that'll take you out to the data set itself. Each of these pages have the same structure. They also have the licensing terms at the bottom. But they obviously all have different content and are kind of structured slightly different or have information in different places depending on what's the best way to do it for the data set. You can come in here and search. It says 119 here. I know it's different than what I said. Let me explain. Some of these include multiple data sets in them. So the example I use here is U.S. boundaries from the Census Bureau. And you can see here, this links out to 10 or so data sets here. So there is a good explanation for that. I'm also a little behind in writing pages for data sets, so hang with me on that. But this is by far the best place to discover our catalog and to look through it. And what's really nice about this is you don't even have to leave the BigQuery console to access this catalog. So if you click the Add Data button here, this will drop you down to 3 options. If you click Explore Public Datasets, this brings you back to that same menu. And the same option. It still has the search function in it. You can sort by category over here on the left. You can also search by keyword. We've done what I think is a decent job of tagging these. If you do find a data set that's not tagged with something you would expect, reach out and we'll update it. But we try for the most part to be pretty comprehensive in our tagging. If you come up here and search geo, as Chad Jennings alluded to in his keynote today, you'll see a list of results here of data sets that have been tagged with that keyword geo. And you can see a list of the data sets that have that in it. Okay, so this is cool, but let's look at a demo. So let's start with something relatively simplistic, right? Is hurricanes by city. And that sounds really easy, but it's actually a little more complex than you would think, and we'll talk about that in a minute. So you can see the query I've written here. It just looks at, okay, find me the location of hurricanes from NOAA's IB tracks, which gives you the internationally agreed upon location of a cyclone at a given time. And show me where their position has been within an urban area, right? So show me when the eye of the storm has entered an urban area in all time. And so in this case, we're going to say, okay, count the number of hurricanes there and give me a list of the returns. Anyone want to take a guess what's number one on the list? Okay, I'll take that as a no. So Houston, okay, that's not a bad guess. And so we'll run it and let's look at our results. So what we're seeing run in the background here is the data set's going through and taking out the geometric point from each hurricane and is comparing that and is determining whether that is held within the polygon that's used to define the urban areas. The number one urban area, Miami, although Houston tied for one. So I'll give you that. I don't have a prize, I'm sorry. I did not think that part through. But now hang on. Urban areas aren't necessarily equivalent to city limits. For instance, the New York City urban area extends down into southern New Jersey. I'll hear debate on whether that's accurate or not, but that's the US Census Bureau and Tiger File's analysis of where that urban area ends, which is very different than New York's city limits. So now let's take a look at that and see what the results will be if we measure that by where has landfall been within the city limits. So we'll pull up from the census places. This gives you the boundary of each city and each incorporated place within the United States. And again, we're just comparing to see that is each point from within the hurricane. So it's constructing the point and the ST geog point. It's taking the latitude and longitude, it's constructing that point, and then it's running it to see if that falls within any of the city limits. So we're matching about 1 million matches or so, just kind of a rough guess. And we'll have an answer here in about 30 seconds or so. Yeah, so here's our answer. It took 29.6 seconds. And we get a very different result. This is looking at just city limits as opposed to urban areas. So what we can see is that we have the flexibility to kind of do the science that we need or do the analysis that we need with these data sets that are in here. And this is great. No one loves tabular data like me. But at the end of the day, looking at tabular data just doesn't really tell a story, right? And that's what we want to do. We want to tell a story. And one of the great things that we can do is we can click out to explore Data Studio. Data Studio is one of our business intelligence tools, similar to other comparable tools. And so here's what you're looking at. It comes in initially as a table, but real quick, we can come out and make a geomap of this. So we'll click on the map over here on the left, or on the right, excuse me. Let me zoom in so that's actually visible. So we'll click on the map here, and we'll just come down and tell our data that, hey, what you think is just a dimension is actually going to be a geo function. So this is going to be geo city. And then we'll just say count hurricanes is our metric. And it'll populate the map here with this with dots that measure for color and size the number of hurricanes. So quickly, let's say I'm an urban planner, for example, right? And I want to tell a story or at least begin to understand what's my risk for hurricanes in my city, let's say Charleston, South Carolina, and where do my risks lie as I make decisions that are going to impact my city over the next 15, 20, 30 years. This isn't the same as talking to a climatologist. That's important to note here. But it is a step in the right direction for someone who's, say, GIS curious and wants to understand, okay, where do I even need to begin to look at my risks? Where do I need to begin to understand what I need to dig deeper into? So this is a relatively quick way to do that, is to take this public data set, click out, do our analysis very quickly in SQL, and click out to Data Studio. But this is limited, right? I mean, there's not a ton of information here. Yeah, I can click on each of these bubbles and see, okay, okay, Jacksonville 5, great. But that only tells so much of a story. And again, I'm a storyteller. I want to be able to tell people kind of what matters. So let's look at the next example then. For this one, let's look at transportation. So let's look at let's change gears. I'm no longer a city planner. It was a quick career shift. I had a good run, but it's time for me to become a taxi driver in New York City. As a taxi driver in New York City, I'm probably pretty busy, but I want to optimize this, right? And I want to look at this in the most efficient way possible, because that's how my mind works. I want to be where I can get the biggest tip on top of my ride, because I'm only going to make so much money on my ride, but I can really make money if I get a high tip percentage. So should I go to downtown? Should I go somewhere where there's going to be longer rides and people are going to tip more? What's the best way to do this? So for this, we'll take a look at all taxi rides in New York City from 2018. And we will look at them by what New York City refers to as their taxi zones. There's 200 some odd of them. And we'll see where the best bang for my buck was. So this is going to go through about 4.7 gigabytes of data. And this will come up here and tell me, okay, well, what's my, and we have our answer in about 5 seconds. Not surprisingly, the airports are the best place to go. Spoiler alert. But again, like this is difficult to understand, right? A multi-polygon of several lines isn't something that we very naturally kind of wrap our heads around as humans. So let's take this out now into BigQuery GeoViz. GeoViz is kind of the lightweight tool that Chad mentioned this morning that's built on top of the BigQuery API that provides kind of a basic visualization for this. As Chad said this morning, is this going to meet all of your GIS needs? No, but it's going to at least be able to give you the tools to say, okay, where do I begin? How do I get started? So we'll take the query over here and we'll run it here. Again, we'll have an answer here in about 5 seconds or so. And once we do, it'll refocus the map into kind of our key area. So right now it's all red. That's not necessarily a great sign. So let's take a look. Okay, so I tell it what my geometry is. And now we'll come down to the style, and let's make it look good. So we'll say data-driven. We'll do this linearly. We'll do it by interval. What's nice about this, about BigQuery GIS or GeoViz, is that you can see it does give you a description of kind of very clearly what each of these mean. So whereas I initially looked at this and said, okay, everything between these values is going to be assigned some gradient of this color. Well, no, data values are actually rounded down to the nearest value domain, and that's how you're assigned the color. So it's nice to have this kind of very detailed understanding of how that's operating. And we'll just do this based on average tip percent. So we'll say 0, God forbid. And just based on my understanding of the data, we'll go with 0.1, so 10%, 11%, 12%, I think you can see this is going, and 14%. You can see this is going. So we'll take a look at this, and we'll assign this some range, right? So we'll assign this, just kind of auto-assign it for now. And what's nice about this is I can look at this and say, okay, well, what now? I have a map, but I still can't actually see where this is in New York. I'm personally, having grown up in Pittsburgh, one, not used to feeling my feet because it's cold outside, but two, not that intimately familiar with New York. So let's adjust kind of the visualization we have here. We'll turn down the fill opacity to 0.25, and now I can kind of very clearly see where I want to be in New York. So this blue area out here, we can click on this, kind of get more detail. Newark Airport, not a surprise, that ends up being one of our higher tip percent range. JFK Airport over here and LaGuardia up here. But if you look, downtown Manhattan also has a pretty high tip percent range. Now, is that because the rides are short and so people just round up to the next dollar, but that ends up being a much bigger impact? Is that because it's mainly business trips? I don't know, but as someone that is kind of doing this analysis, I know that BigQuery GeoViz can now enable me to say, what's next? I want to dig into that. You know, there's fewer and fewer scientific discoveries these days are made with a eureka moment. I think they all kind of start with this, that's really interesting. How can I dig into that more moment?
So this is really interesting. How people are taking taxis to these islands over here?
That's all JFK.
That's all JFK. or Jamaica Bay too. Also, maybe James Bond is driving a taxi these days. I don't know. Maybe it's the flying cars we've all been promised. So yeah, so I can look at it and say, okay, I don't know all the answers after a 5-minute analysis and a quick overview in BigQuery GeoViz. But what I do know is where I want to drill down more, because no one has the time to drill down everywhere. No one has the time to drill down in every taxi zone. But we can look at the ways that people move about cities much faster, and we can understand how this impacts people's lives. But New York has a really extensive public transit system, especially in Manhattan. So my next question is, well, is there a correlation between where people are taking taxis and where they have access to the subway? Lucky for you, I got a chance to onboard New York City subway data last night, which I know everyone is just over the moon excited about. So let's take a look at riders by year going back to 2013 by borough, which I think is a really interesting way to look at it. So I'm just calling, okay, for a given station, is it within this borough? It was much faster than I thought it would be. Not a bad problem to have. So I can look up here, and in full disclosure, Staten Island, we didn't onboard the Staten Island Railroad stuff. I did have to go to bed at some point. So these are the rider numbers we have. And what's interesting here is that Manhattan is by far it sees the most riders, which is really intriguing because it also sees by far the most taxi drivers or the most taxi rides. It also sees the highest tip percentage in taxis. So there's a story that's starting to unfold here of how do people move around New York City, and how does access to these transit means and these transportation means change the way that people view the world and people experience the world. Let's also look at a factor that may be driving this. Maybe Manhattan has more riders in the transit system because they have more transit stations. I mean, it makes sense, right? I'm lazy. If the less distance I have to walk, the more likely I am to take public transit. So let's take a look at subway stops by area of each borough. So this looks at the total number of stations and divides by the square area, the square meters of each borough. So I'll run a width statement up here that just allows me to do that aggregation before I call in the geometry. And my query results didn't show what I expected them to. Okay, so the count stations, probably not particularly accurate, but if you look, Manhattan tends to have more stations by area. So is there an impact of having more stations in Manhattan that drives more ridership? Or is that driving so many people that some people are opting to take taxis more frequently? Again, I'm not going to have the answers after 5 minutes of looking at this, but I have the answer of where to go next and what to explore next. Okay, let's shift to something that is very near and dear to my heart, both for past and future purposes. A little note about myself is that I typically only do demos in states in which I've lived. Having 13 addresses in the last 11 years makes that a lot easier than it sounds. But one of the states in which I lived was Oklahoma. And so let's take a look at, something very famous that happened in Oklahoma, tornadoes. Now, I was fortunate in my year and a half in Oklahoma not to have seen a tornado, although there were some nasty funnel clouds a friend of mine saw. And so let's take a look at all the places where tornadoes have crossed roads in Oklahoma between 2007 and 2017, which is the latest year the National Weather Service has data available for tornado paths. So this is calling on two different tables here, one of which is something I'm really excited to highlight. It's this table right here. This is our all roads data set. I've mentioned this at every opportunity I've had today because I'm very excited about it. But this is all roads within the United States. So it's alleys, it's primary and secondary roads, which tend to be divided highways, but it's also alleys, it's driveways, it's private roads, it's four-wheel drive roads, which I don't know how they differentiate between that and an alley, but they do. This is every road in the United States is in this table. We also have them broken out by state if you're looking for something that's a little more manageable, or you're just kind of looking, you already know kind of that predefined area. The state tables are named by FIPS codes. If you don't have your state FIPS codes memorized, I don't have all 50 states memorized, so adding FIPS codes on top of that is a bridge too far. Don't worry, we also have FIPS codes available in the Public Datasets program. So let's take a look at this and see where every place where a tornado has crossed a road. And one of the fun things about this is maybe I'll get an answer I wasn't expecting. I expect that there's been a lot of tornadoes that have crossed roads. But what I might see is something that I wasn't anticipating seeing in the first place, or maybe I wasn't originally looking for. But being able to take this data that's more easily accessible now and being able to visualize it kind of gives me access to that. So as a note here, that table the all roads table is about 9 or so gigabytes in size. And as you can see, this query processes 8.3 gigabytes, but because of the way we've clustered the tables and partitioned them, by telling it, okay, I only want this state from that all roads table, we've run under 500 megabytes that were actually processed. So out of the 8.3 gigabytes that are in the tables, we only are billed for a little under 500 megabytes of that. So a really powerful capability to kind of work within whatever means your research group has. So we can look down here and see the results. But again, there's a lot of line strings, of polygons, and I don't know about you, but that isn't the way my mind works. So let's go back out to GeoViz, and let's just kind of go in a totally different direction than taxis in New York. And let's run this query. And what we'll see is this map will zoom out and then zoom back into Oklahoma. And we can see here we've only mapped the tornado paths as opposed to mapping the roads, mostly because they're on the base layer of the map. But there's something really interesting about this map that isn't what I was looking for. What I was originally looking for is I just want to see every tornado across the road. Maybe I work for the state's Department of Transportation, and I need to better understand where to build an overpass as opposed to tunnel. Tunnels are a lot more expensive, but if you don't have to rebuild them every 5 years, maybe it's more affordable in the long run. But there's something very distinct about this map, and I'm sure most of you have seen it. Tornadoes in Oklahoma in the last 10 years have tended to move southwest to northeast. That's a very specific pattern across a very large and diverse geographic area. The southwestern portion down by Lawton, Oklahoma, has what Oklahoma calls mountains, what those of you that live in the Rockies would call large hills. But they tend to break up storms, and they tend to see different weather patterns there, as opposed to moving straight east, which is kind of plain lands in southeast, as opposed to moving north, which tends to be a little more urban, and in Tulsa and Norman, in Stillwater, in Oklahoma City. And all of them had this like very distinctive pattern of how tornadoes move across the state. So I came here looking for one answer, and now I have a totally different answer. Is there something I could do with this? Maybe if I'm an emergency manager in a community and I'm trying to help people understand how their risk changes in different parts of the country or in different parts of the state. Maybe if I'm an insurance company that's trying to say, hey, here's why we set your rates the way we did, and here's how you can be safer, and also, by coincidence, save money on your insurance too. So again, it gives me an answer I wasn't looking for, and gives me a whole new story to tell, and a whole new story to explore. So I think that the BigQuery side of this is a very different take on things than has been possible in the past, especially with BigQuery GIS. Chad hit the nail on the head this morning, in my opinion, when he said that we're at an inflection point right now of being able to do things that we weren't able to do in the past. But not all data is tabular, right? And I mentioned earlier we have 8 to 9 petabytes of data in Google Cloud Storage, mostly satellite data. So we're looking at things like geostationary satellites, Sentinel and Landsat, weather models, the National Renewable Energy Lab's Solar Radiance database, and I want to make sure that we touch on that as well. Now, one thing we do that does tie back to the beginning of this is we parse out, especially for NetCDF or HDF files, we parse out the metadata out of those and make it available in BigQuery so that you don't have to learn the file naming scheme for every single data type you want to use. If you know, let's say, the bounding box and the date time that you want to look at, you can come down here and you can say, okay, I want to look at NOAA goes. So I'll come down here to go 16. There's a description here. I'll zoom out a little bit. So there's a description here. And then as I go down to each of these tables, you can see here's the metadata for every file that's in GCS. Now what's nice about this is it also provides you the dataset names. You can call that through APIs. It also gives you the direct link in GCS to that dataset. So you can use this to subset the data, this kind of 100 of terabytes bordering on petabytes, lowercase a archive of GOES data, as opposed to the official kind of record archive of GOES data. And you can use this to subset your analysis. Let's say, for example, you wanted to see how a volcanic eruption might change air quality in an area. And yeah, we could grab air quality data, and that would tell a pretty terrifying story. But let's look at the volcanic eruption that occurred in Hawaii about 1.5 years ago. The air quality data from there, specifically the sulfur dioxide rates, spiked on May 30th, or excuse me, May 27th, 28th. Typically hovering between 5 and 10 parts per million, up over 45 and 50 as the eruption kind of reached its full power. And so let's take a look at what that kind of difference looks like from a satellite perspective. So I have my handy Python notebook here. I'm just going to write this code on the fly. Okay, I'm done. And so let's open up a virtual machine. I'm going to open one up that I have pre-built. But what you could do is you could even use the console cloud shell that's available here. This provisions you a single VM for free. And allows you to kind of have that full interactive experience that you would have in a VM. It's obviously limited in its compute capability, and so if you have kind of more than like this kind of one-off need, I would encourage you to go out to the full VM. But if you'd like to follow along, or if you'd like to try this afterwards, again, we'll make sure that the code for this is available, and you can kind of try this on your own. In the interest of full disclosure, I am standing on the shoulders of those that came before me in this. The original demo for this kind of came from was built entirely by a gentleman named Lack. For those of you that have heard of Lack, he is a rock star. For those of you that haven't, he's a rock star. But he was a huge help in helping me build this demo, and I want to acknowledge that before I go too far and forget to do so. So I'm going to click over here to my virtual machine that I provisioned, and this is just a standard size virtual machine. It's roughly equivalent to what you'd get in the Cloud Shell console. So we'll connect that here and we'll SSH into our VM. And as soon as this comes up, we'll get started. There's been some kind of magic behind the scenes of installing libraries and whatnot. I can make sure that we get something out there as well so you know what libraries to install. But for the most part, let's go right into executing our Python. So I'll come over here and I'm just going to go through this kind of chunk by chunk. Line by line seems extraordinarily painful. So this first group is designed to list objects in GCS. Yeah, bigger font. Yeah. You'd think having sat in the earlier sessions where I couldn't see from the back, I would remember that. No. So this first one just defines a function that says, for a given list of criteria, grab the name of the files from GCS that match those criteria. So in this case, I've come down and I've named the bucket, which is the public bucket that contains GOES 16 data. I've given it a prefix. I've kind of hard-coded this because I know what date I want to look at. But again, this is something that you could determine based on pattern matching in BigQuery. And then I want you to give me this list of blobs, of objects. So I want to do this both for the beginning of the eruption or during the eruption, and I want to do this for before. And so I've pulled a day from about a year in advance. The satellite launched in late 2016, so data started to become available in mid to late 17. So unfortunately, I don't have a full year in advance, but it's close enough. And so you'll still get the idea of what that looks like. So we'll come down here. We'll define a couple variables at the top too that just says, hey, when I say GOES bucket, here's what I mean. And we'll run this, and we will pray that the tech demo Murphy has left the room. Okay, so far so good. Nothing's yelled at me yet. So in here, and I can print this list, and I can say, okay, here's this list of blobs that came from during the eruption, right? Okay, we have one. That's all I need. And so we can come up here and say, here's the list from before. So far, so good. I can, absolutely. Okay, so is that good back there? Cool. Yeah, so I have the blobs I need, or at least I have the names of them, right? But because these are NetCDF, and the current standards for NetCDF don't support kind of the ability to unwrap on the fly, I've got to download these files locally to work with them. But that's okay, I can download them to the VM and work with them there. So now I'll define this to say, okay, for everything that matches this pattern, download it to my local VM. All right, that's a little snarky VM. I know I like Cookie Monster GIFs, but maybe not right now. Maybe not right now. Not right now. But okay, so I've got the files downloaded, right? And I can do. Oh yeah. So I can do this, right? And I can see, okay, here's the folder I created, and as I drill down, I'll see here's the subdirectories I created, and here's the files I have. Cool. So far, so good. Let's crop the images now to only show our area of interest. Now this is tricky. Go16 sits over the eastern half of the Western Hemisphere, so roughly the eastern seaboard of the United States. Now, both of these satellites, both Ghost satellites, do take a full disk scan that gives you just about the entire Western Hemisphere. The satellite actually moved in between images, which is not typically what a geostationary satellite would do, hence the stationary part of geostationary. But it moved from its test position into its operational position. So we'll have to kind of sugarcoat this a little bit and kind of work with it to make it work. But it does work, much to Simon's concern in the back. And so what you'll see is the second image is just on the edge of the imagery, but it is included. So we'll define the cropping of the imagery, and you'll see here that we have two different standards set for two different before and after subpoints. So there is a lot of code here. Also, what's also happening here is you can see this in the comments. So we're kind of reprojecting these grids. I don't have a whole ton of time, so I won't kind of get into that too far. But this is basically how we get everything to talk about the Earth in the same way on the same geometry. So there's some reprojection here, there's some subsetting, and then there's also some cropping in here as well. So let's go ahead and run this. And I've now cropped and replaced my local files using the downloads that I ran. So okay, cool. Nothing's yelled at me yet. I'm going to keep going. And now I'm going to define the image. So this tells me which variables I want to plot, how I want to define the colors in the visualization. Now, when I first designed this demo, I got on a phone call with LAC and was like, "Hey, man, something's wrong." I was like, "These colors are way too different." And we went through and we changed a bunch of color settings and got the exact same result. And so it was a lesson in, one, being humble enough to reach out and ask for help when I need it. But two, of saying, hey, sometimes your results are right, even if you don't think they are. And so I'll come down here, I'll just define this function, and I'll define a function that writes the files out to GCS too, so I don't have to worry about losing them, especially if I want to get rid of my VM after this. So all this does is pick up a given file, move it to GCS, Google Cloud Storage. And the final one will be, okay, take those two functions and take this NetCDF image, convert it to JPEG, and then move it over to GCS. So come down here. I have a multi-convert as well that just kind of runs this over multiple files. So far, so good. And let's run it. So this is going to take a minute. I'll kind of give you the summary spiel before we get out of here. So let's go ahead and run these. They'll take a minute. Keep in mind they're processing 4 chunks of high-resolution satellite data over a very fine granularity. So Once those are done, we'll pull up, and I want to show you kind of the very stark difference between the before and after. Spoiler alert, there was more pollutants in the air after the volcano erupted than before. And so as that processes, I'll kind of go back and just say that, we're working really hard to make life a little bit easier for folks and to make it easier for what you do best, and what you can do most efficiently and most effectively with your time. My guess is that everybody in the room managing the same data set in duplicate is probably not that. My guess is everyone doing science on the same data set that they don't have to manage in duplicate, that's probably more efficient. And so the goal here is for us just to make life a little easier and make you a little more effective and capable in your job. So it looks like the first one of these ran. What's that? Of course.
Excellent segue in the saying that in a few weeks, with Kurt's help, we're actually going to have Go's data in Earth Engine. So about the last 2/3 of this script will not be necessary so much. They will be necessary if you want to work on something which is not in Earth Engine, like HR data.
Yeah. And Kurt's done an awesome job on that. But Kurt, actually, I'm going to point this out here, identified an error in the netcdf files. And we were able to reach back out to NOAA and one, kind of build a workaround in the meantime, but also kind of make them aware of an issue they were already aware of, it turns out, and kind of work with them on a resolution. So shout out to Kurt on that. That's really impressive. And I think that's, from NOAA's perspective, having spoken with them about this, what they say is that means that everybody gets better data and everyone gets better scientific data and cleaner data. And so that's kind of the benefit, one of the benefits that they see out of something like this as well. So pull these up. These are still running. These might take a bit, and I'm coming up on time here. About 5 minutes left, but I do want to leave time for questions. So let's start with that, and then as these finish, I'll go ahead and put them up on the screen. If you do have a question, we are recording the session, so I just ask that you speak into the mic. Simon, can I volunteer you to do so?
Thank you. Early on, you mentioned the new dataset HRRR or HER.
Yep.
You call it unstructured. Could you talk about why you call it unstructured? It's a gridded data for the CONAS at some uniform spatial temporal resolution. And I quickly looked up, saw it was GRIB format. Could you talk about a little bit to see why it's unstructured?
Yeah, so when I say unstructured, I'm thinking of the difference between like an image and a tabular data set, as opposed to have the proper metadata and gridding and structure that go in a GRIB file like that into place. So yeah, that's a great point. It is a well-structured data set, but I'm thinking of the difference between like image and tabular data when I say that. So anything that kind of doesn't make sense in BigQuery goes out into Google Cloud Storage. And so that tends to be mostly imagery data right now.
Hi, yeah, thanks very much and for everything you've done. It's really helpful to have all this stuff available. One thing, kind of an observation, which is a very good reason for it, is that some of the data that's not just satellite data is quite US centric, and I can understand why that would be.
Sure.
But I suppose the question is, how do you come to the situation where you get the data, and is there anything that we could do more remotely to kind of recommend data sets that you would look at, or how does it work?
Yeah, I mean, I love to hear community feedback of data sets you want, because the whole point of this is to serve the community and to provide for the needs. So like, yeah, having that very direct feedback is very helpful. Yeah, most of our kind of non-satellite data sets tend to be US centric. I think there's a lot that goes into that. Part of it is that it's really easy to go get US boundaries from a single census bureau as opposed and cover like a really large area, as opposed to having to go to maybe the Census Bureau for one thing. I'll just pick Australia, for example, because I had to call someone about this the other day, and then kind of go to other agencies and I don't understand as well. But we are working with some groups right now to do some things that I don't want to jinx it. I don't want to give too much out here right now, but we're having some discussions about how we can do so on a global scale at a much more scalable means than having to go through each individual country, because that, frankly, like just it's going to take a while, right? And the longer you wait, the more work you have to do. And so we're trying to figure out a way to do it at a much larger scale, much faster than. So the short answer to your question is stay tuned. You can see updates in GCP Marketplace. This is a shameless plug, but you can follow me on Twitter. I'll post updates there as well. Yeah, so it's definitely on our minds though. Yeah, and I appreciate you mentioning that.
Can people upload their own data into BigQuery?
Yes, absolutely. Yeah. So one of the nice things about BigQuery is that every user gets 10 gigabytes of free storage. That's a lot of tabular data. So you can upload that and share it, and make it public. The nice part about that is you aren't paying for their queries. So the person who runs the query, they're billed for that query. So if you make it public and someone you've never even imagined possible using your data uses it, you're not charged for that. So you're only charged for the storage of that. And then obviously if you run queries on top of that, you're charged for that as well.
Thanks for the overview. It's very nice. And I will follow you on Twitter.
Excellent.
But I just wanted to ask you, so it seems like one of your data contributors is the National Institutes of Health.
Mhm.
So for instance, if we were to make our own data sets in here, would that be HIPAA compliant? Like, does it sort of safeguard patient safety, this platform, or not really?
So
De-identified, I mean, obviously, but
yeah, so we look to the data providers to make sure that the de-identification was done properly. And this kind of goes back to what we talked about earlier of reaching out to data providers for their expertise. I just don't know enough about the appropriate means to de-identify healthcare data to make that determination. Um, we can work with you on, okay, hey, if you say these are steps we need to take, we can help you take those steps. Um, and if it's de-identified, then I think we can figure something out. But yeah, it's very difficult for me on my end to say, okay, this is definitely HIPAA compliant, because I just don't know enough about the space. We are working with a team right now from the healthcare life sciences side of Google Cloud to onboard one more data sets around healthcare life sciences in genomics, and they are bringing some of that expertise and stewardship to the table. So I'm hopeful we can expedite that process. But yeah, I think we can work with you on it. But making that promise is just not one I'm sure I can keep.
Thanks.
Sorry if this was already covered, but do we have to access these through BigQuery?
So the data sets that are stored in BigQuery, yes. You don't necessarily have to go through the web UI. You could go through the command line or something else. And you can pull data out once if you say, okay, I want to look at this subset of a data set. Once you get those results, BigQuery enables you. I don't not have a BigQuery tab open. This might be the first time ever. BigQuery enables you to come down and say, okay, let me grab those results and let me make those download as a CSV to my local file, save to Google Drive, whatever. For the data sets that are in Google Cloud Storage, no. I would one of the challenges I think we're helping unlock here is that it takes a long time to download huge archives of data, right? I don't think that's news to anybody in this room. And part of the reason for that is that the internet's kind of like a water spigot, in that you'll only get as much flow as kind of the narrowest point in your pipeline, right? So weakest link in a chain kind of thing. And if you could get, I don't know, a gigabyte down out of GCS, but your local speed is like 100 megabytes, you're only going to get 100 megabytes down at a time. So you probably haven't solved kind of the end problem for yourself, that it takes a while to get access to these data.
Can I jump in here?
Yeah.
So we often get this question on the Earth Engine side, and our usual follow-up question is, what are you going to do next with your data? Because if you're going to download more than a few images, you probably want to do some kind of processing. So tell us what kind of processing you want to do. If we can do it already, we can show you how. If we don't know how to do it, we would like to know what the use case is.
Yeah, I think that's one of the great things about this is we all like to learn too. So yes, you can bring it down. My personal opinion is that it's just much faster to do it in the cloud. But I recognize I'm biased here. So, and I forgot that I had set this up a little bit like a cooking show, where I magically put my pie in the oven and then turned around and, oh, I happen to have one finished already. So I actually cheated a little bit and have the previously made versions of this image that we're producing right now. So let's go ahead and pull this up. This first one is from before. So the center of our image here is the center of the volcano. red is bad, obviously, right? Red and pink are colors we don't want to see given that we're measuring particulate matter in the air. So this is before, and hey, look, there's a hurricane here or a volcano here. You're gonna see some pollutants in the air, right? I mean, that's kind of how volcanoes work. And so let's take a look at one of the after pictures. And I'll warn you that I mentioned that the satellite moved kind of in between these images. So the left half of it is cropped off because it moved just enough to take away like half of the image, but not the whole thing. But you'll get the point pretty quickly. So this is the morning of the eruption. The volcano erupted and sent ash and smoke about 30,000 feet in the air. And from a satellite view, this is what that looked like. This is a story. Okay, this difference right here, this is how you get the attention of someone like me who's not an expert in the data, who doesn't understand the extreme specifics of this, but this is the story we want to help tell. The stories that change matters and that these things are important to make a difference. And we want to enable you and empower you to tell that story, to communicate your research, and to do it as quickly as possible. So I'm at time here. I'm actually a little over time, but I appreciate everyone coming out today. I'll be here the rest of the day. Unfortunately, I'm not able to be here tomorrow, but I would love to chat with anybody after the session or later today if you'd like. Thank you very much.